Hello, welcome to another wacky episode of The Solid Brothers featuring your pal Phil. Today is a severe fuck up where I forgot to record my voice. This is the second time I've done that in this series. So you can blame whatever you want, but marijuana? Today's going to be a exciting episode where you'll watch menial unimportant information and I'll read menial important information. In other words, today Colton Phillips reads the Wikipedia article. The Wikipedia article of citric acid cycle. The citric acid cycle, also known as the tricarboxyl acid cycle or the Krebs cycle, is a series of chemical reactions used by all aerobic organisms to generate energy through the oxidation of acetate derived from carbohydrates, fats, and proteins into carbon dioxide and chemical energy in the form of adenosine triphosphate, ATP. In addition, the cycle provides precursors of certain amino acids, as well as the reducing agent NADH. It is used in numerous other biochemical reactions. Its general importance to many biochemical pathways suggests that it is one of the earliest established components of cellular metabolism and may have originated abiogenically. The name of this metabolic pathway is derived from citric acid, a type of tricarboxylic acid that is consumed and then regenerated by this sequence of reactions to complete the cycle. In addition, the cycle consumes acetate in the form of acetyl-CoA, and water reduces NAD+ to NADH and produces carbon dioxide as a waste byproduct. The NADH generated by the TCA cycle is fed into the oxidative phosphorylation electron transport pathway. The net result of these two closely linked pathways is the oxidation of nutrients to produce useful chemical energy in the form of ATP. In eukaryotic cells, the citric acid cycle occurs in the matrix of the mitochondrion. In prokaryotic cells, such as bacteria, which lack mitochondria, the TCA reaction sequence is performed in the cytosol, with the proton gradient for ATP production being across the cell's surface, rather than in the inner membrane of the mitochondria. Several of the components and reactions of the citric acid cycle were established in the 1930s by the research of the Nobel laureate Albert Gheorghe, for which he received the Nobel Prize in 1937 for his discoveries pertaining to fumaric acid, a key component of the cycle. The citric acid cycle itself was finally identified in 1937 by Hans Adolf Krebs while at the University of Sheffield, for which he received the Nobel Prize for Physiology or Medicine in 1953. Components of the TCA cycle were derived from anaerobic bacteria, and the TCA cycle itself may have evolved more than once. Theoretically, there are several alternatives to the TCA cycle. However, the TCA cycle appears to be the most efficient. If several TCA alternatives have evolved independently, they all appear to have converged to the TCA cycle. The citric acid cycle is a key metabolic pathway that unifies carbohydrate, fat, and protein metabolisms. The reactions of the cycle are carried out by the 8 enzymes that completely oxidize acetyl-CoA into molecules of carbon dioxide. Though catabolism of sugars, fats, and proteins, a 2-carbon organic product, acetate in the form of acetyl-CoA, is produced, which enters the citric acid cycle. The reactions of the cycle also converts 3 equivalent of nicotinamide, adenine, or NAD+, into 3 equivalents of reduced NAD+, bracket NADH, one equivalent of flavin adenine dinucleotide, or FAD, into one equivalent of FADH2, and one equivalent each of guanosine diphosphate, GDP, and inorganic phosphate, PI, into one equivalent of guanosine triphosphate, GTP. The NADH and FADH2 generated by the citric acid cycle are in turn used by the oxidative phosphorylation pathway to generate energy-rich adenosine triphosphate, ATP. One of the primary sources of acetyl-CoA is from the breakdown of sugars by glycolysis, which yields pyruvate that in turn is decarboxylated by the enzyme pyruvate dehydrogenase, generating acetyl-CoA according to the following reaction scheme. A doodly doodly. The product of this reaction, acetyl-CoA, is the starting point for the citric acid cycle. Acetyl-CoA may also be obtained from the oxidation of fatty acids. Below is the schematic outline of this cycle. The citric acid cycle begins with the transfer of a 2-carbon acetyl group from acetyl-CoA to the 4-carbon acceptor compound oxaloacetate to form a 6-carbon compound citrate. The citrate then goes through a carbon... The citrate then goes through a series of chemical transformations, losing 2 carboxyl groups as CO2. The carbons lost as CO2 originate from what was oxaloacetate, not directly from acetyl-CoA. The carbons donated by acetyl-CoA become part of the oxaloacetate carbon backbone after the first turn of the citric acid cycle. It's like a wheel or something. Loss of the acetyl-CoA donated carbons as CO2 requires several turns of the citric acid cycle. However, because of the role of the citric acid cycle in anabolism, they might be lost, since many TCA cycle intermediates are also used as precursors for the biosynthesis of other molecules. Most of the energy made available by the oxidative steps of the cycle is transformed as energy-rich electrons to NAD+, forming NADH. For each acetyl group that enters the citric acid cycle, 3 molecules of NADH are produced. Electrons are also transferred to the electron acceptor Q, forming QH2. At the end of each cycle, the 4-carbon oxaloacetate has been regenerated, and the cycle continues forever and ever. Steps. 2 carbon atoms are oxidized to CO2. The energy from these reactions is being transferred to other metabolic processes by GTP or ATP, and electrons in NADH and QHT. The NADH generated in the TCA cycle may later donate its electrons in oxidative phosphorylation to drive ATP synthesis. FADH2 is covalently attached to succinate dehydrogenase, an enzyme functioning both in the TCA cycle and the mitochondrial electron transport chain in oxidative phosphorylation. Yo man, that's a phosphorylation, not phosphorylation. What's up? FADH2 therefore facilitates transfers of electrons to coenzyme Q, which is the final electron acceptor of the reaction catalyzed by the succinate ubiquinone oxidoreductase complex, also by acting as an intermediate in the electron transport chain. The citric acid cycle is very complicated, but that's fine. Mitochondria in animals, including humans, possess 2 succinyl-CoA synthetases, one that produces GTP from GDP, and another that produces ATP from ADP. Plants have the same types of produces, like these things, mong-mongs, but twing 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 twing. Twing 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 twing. A twing 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 twing. A twing twing twing. The total number of ATP generated from a complete oxidation of 1 glucose into glycolysis, citric acid cycle, and the oxidative phosphorylation is estimated between 30 and 38, but you might as well say it's about 32. Basically, it's 32. The theoretical maximum yield of ATP through oxidation of 1 molecule of glucose in glycolysis, citric acid cycle, and oxidative phosphorylation, it's not phosphorylation, it's phosphorylation, is 38, assuming 3 molar equivalents of ATP per equivalent NADH and 2 ATP per FADH2. In eukaryotes, 2 equivalents of NADH are generated in glycolysis, which takes place in the cytoplasm. Transports of these 2 equivalents into the mitochondria consume 2 equivalents of ATP, thus reducing the net production of ATP to 36. Furthermore, inefficiencies in oxidative phosphorylation due to leakages of protons across of the mitochondrial membrane and slippages of the ATP synthase proton pump commonly reduce the ATP yield from NADH and FADH2 to less than the theoretical maximum yield. Obviously, then the observed yields are therefore closer to about 2.5 ATP per NADH and about 1.5 ATP per FADH2, further reducing the total net production of ATP to approximately 30. In an assessment of the total yield of ATP from newly revised proton to ATP ratios provides an estimate of 90 to 99 per glucose, and that's about 30. But there's still good news. You'll have to see it next time on the Solid Bros. As for now, you've seen me walk through pipes, get into some fights, see a Yoshi, ride at Yoshi, get some cookies, and fuck right off, because next time on the Solar Bros, we won't be talking about the citric acid cycle now, will we? Peace. Oh, fuck.